Welcome everyone to this first lecture in the framework of the 40 under 40 lecture series on combustion. It is my really great pleasure to welcome Professor Hessam Babaee from University of Pittsburgh. And I will briefly introduce Hessam, thanking him again for having accepted our invitation, and then I will give him the floor to present his research. Professor Hessam Babaee is the assistant professor at the University of Pittsburgh in the Department of Mechanical Engineering and Material Science. He has obtained his PhD in Mechanical Engineering and the Master of Sciences in Applied Mathematics from Louisiana State University in 2013. And then he joined the Mechanical Engineering Department at the MIT for his postdoctoral research, where he worked on stochastic reduced order modeling. He then joined in 2017 the University of Pittsburgh, and his research focuses on reduced order modeling and machine learning techniques for a variety of problems. His research has received many fundings, among them NASA, the National Science Foundation, the National Institute of Health, and the Air Force Office for Scientific Research. Today, Hessam will talk about his research on-the-fly low-rank approximation for turbulent combustion using time-dependent subspaces. Thank you very much, Hessam, for accepting the invitation, and I leave you the floor. I will allow you to actually do so. And
yeah, thank you so much. Yeah, I think I should be able to present the screen.
Yes, everything works correctly.
All right, thank you so much for the kind invitation. It's an honor to present in this prestigious lecture series. So yeah, I would like to share some of the progress we've made using time-dependent bases and application of that to turbulent combustion. Really the motivation here, this is a turbulent reactive flow, and you see the structures and correlation. And what I also showed was this is a very simple demonstration of time-dependent basis for capturing the subspace, the low-rank subspace of this uncertain parameters of this. This is a Russell dynamical system, and you see this time-dependent subspace tracks these random samples of this dynamical system. So this application of time-dependent basis to uncertainty quantification, and so I'll show you how you can use the same principle for turbulent combustion. So this is, I wanted to acknowledge the students in my group contributed to this, and also my collaborators who have contributed also to the talk as well, including Dr. Jackie Chen and Dr. Daniel Levesco and the others, and Dr. Payman Gibby at the University of Pittsburgh. All right, so the motivation is, one of the motivation for using on-the-fly low-rank approximation is turbulent combustion, where we have to solve this species transport equation. For complex fuels, you can have a large number of species. So obviously this large number of species poses all kinds of computational issues, including among them the fact that we have to basically solve order of 1,000 or very large number of PDEs coupled together. So this requires a lot of CPU costs as well as memory costs. This is a quote from actually a paper that 10 years ago from Dr. Jackie Chen's group, that this massive DNS numerical simulation of combustion, because of just IO limitations, at the time they could only store every 400 time steps, but there are things happening that are order of 10 simulation time steps. So this alone just shows you a sense of the difficulty and the challenge of doing combustion for a large number of species. So this presentation is about taking the very basic steps and first steps in trying to use these time-dependent basis to also resolve these issues. So this is the layout of my talk. I'll first give an overview of on-the-fly low-rank approximation using time-dependent basis, the mathematical principles, and I'll try to present that in a generic form. Then I'll show you application of that to do sensitivity analysis. And then I'll show the application of the turbulent combustion. And then I'll show you some of the recent work that we have done in terms of reducing the cost of applying this time-dependent subspace to turbulent combustion. So, and in the last example, I'll show you UQ example as well as turbulent combustion. So let me give you an overview of time-dependent basis. So perhaps the most important thing is to first understand the application of time-dependent basis. The application of time-dependent basis is for reducing the cost or reduce or modeling of doing of nonlinear matrix differential equation. So this is not vector evolution equations like POD type reduce or modeling. This applies to matrix differential equation. And so a matrix differential equation, as its name implied, it's an evolution equation for a matrix. And in fact, combustion is one problem that can be formulated as a matrix differential equation, where each column of this matrix is the species, a mass fraction of a particular species. And if these species are instantaneously correlated, that means if their instantaneous SVD decays quickly, then you can approximate it with an SVD-like decomposition, instantaneous SVD-like decomposition, where these are a set of orthonormal modes in the physical space. And this is a matrix of singular values, but it's not diagonal. This particular form of low-rank approximation with time-dependent basis, but it can be rotated to a diagonal form. And these are a set of orthonormal vectors in the composition space. So if this matrix is a matrix of mass fraction, each column is a different species, and these vectors, each of these vectors is a vector in the composition space. And if these are low rank, then hopefully we can approximate these NS with R that is much smaller than NS. Okay, so this is an application to turbulent combustion. You can also think of an application to uncertain quantification of a dynamical system where these columns could be random samples of that system. And again, if these random samples are instantaneously from each other, then you can also approximate like that. Or these samples could be the uncertainty of the governing equation with respect to a set of parameters. And that, again, in that case, you can still represent that system as a matrix differential equation. I will talk about all these three examples during my lecture. But I want to frame all of them as just matrix differential equation. Okay, so if you look at this, is instantaneous SVD-like decomposition, but we will not actually perform SVD. And so this is important because if you want to perform SVD, you have to first solve the equation and then being able to perform, do dimension reduction and do posterior analysis. But the idea is to derive evolution equation for all these three components. As you will see, we formulate a variational principle to derive evolution equation for all these three components. And so this is based on Riemannian optimization and the fact that a matrix of rank R belongs to a smooth surface of all matrices. And so what this amounts to evolution of the components, it amounts to evolution of the tangent space to this nonlinear manifold, where this nonlinear manifold is the space of all rank R matrices. All right, so there is really beautiful mathematics behind this on-the-fly low-rank approximation. I just want to touch on that these are based on tangent spaces. But what is important and probably different from other reducer modeling is that this kind of reducer modeling doesn't require any data beyond knowing the initial condition, the boundary condition. So that, in fact, you can actually derive this evolution equation without generating any data. So this is unlike other, like POD or PCA type dimension reduction, where you have to first generate the data and then perform the reducer modeling. Because as you will see, we will actually derive evolution equation for all these three components. So this is not reducer modeling. And so that's, I think, an important distinction to keep in mind as we move forward. we do to know the accuracy of this methodology after we solve this equation, we also solve the full order model. That means we solve all of these columns. If possible, for some of these cases, we cannot actually solve the full order model because the number of columns are massive. But for those that we can, then we will actually perform SVD after the computation to compare against this kind of reduced order modeling, because instantaneous SVD of this matrix would be the optimal low rank approximation at any given time. So after we solve this simulation, we go back and compare our reduced order modeling results against the optimal. And in my slides, you will see instantaneous SVD in some slides, or you see instantaneous PCA. By instantaneous PCA, instantaneous SVD, we mean we actually solve the full order model equation, we perform instantaneous SVD, and then we're comparing our results against that. So I want to clarify that right now. But like I said, this doesn't require any data, and because it doesn't require any data, because it's not trained for any kind of data, so then one of the nice things is that so it can adapt on the fly to any changes. So if you change the boundary condition, or Reynolds number or Mach number or some other parameters, you really, because the data generation is not even involved in the process of reduced order modeling, so I can adapt. So basically, we are solving the PDE directly, just in this compressed form. Instead of solving for all of these species, we solve it in this form. And because of its connection to SVD, instantaneous SVD, it's interpretable. We know how to interpret SVD. We know how to interpret these vectors. These vectors would be a vector in this position space, and each one of these components is the weight for a particular species. And so we can interpret this in the context of turbulent combustion. So a little bit of historical notes. In fact, this kind of methodology has been used in the past and was developed in the quantum chemistry community. This is a fantastic paper for solving Schrödinger equation, for solving high-dimensional equation. And then in the applied mathematics community, this was put in more generic context, and it's named dynamical low-rank approximation. In the UQ community, where my work actually was initiated, this kind of low-rank approximation, where you here in this kind of formulation, you have a triple decomposition, but in my slides you also see a bi-decomposition, that this matrix is decomposed to two matrices as opposed to three matrices. This was first developed in the context of uncertainty quantification, known as dynamically orthogonal decomposition, and then other variations of that were developed. So the OTD, for example, that I will show some slides on, is the application of this kind of dimension reduction to linear system for sensitivity analysis and other variations. But what is important to keep in mind is that, and we showed that in this paper, that this triple decomposition and these two decomposition, bi-decompositions are exactly equivalent. What do I mean by equivalent? That means this low-rank matrix that we approximate is exactly the same, whether you formulate it as a triple matrices or two bi-matrices. In fact, you can absorb this sigma. You can see all of these bi-matrices. You can absorb this sigma either into U or into Y and get different flavors of this. But you can do it with different constraints and so on and so forth. So what is important is not to get lost on the fact that these are three matrices multiplication or two matrices multiplication. What is important is that all of these are based on time-dependent subspaces, meaning this matrix is evolving. This would be a subspace correspond to the columns of that matrix. In the context of combustion, the columns would correspond to the physical space, and this would correspond to the species, the composition space. And so both of these subspaces, which are the row space of the matrix, both of them are evolved. But this was a little bit of a background on time-dependent basis. So an application of how you actually derive this and all those elements for sensitivity equation. So why sensitivity equation? Sensitivity equation, if you want to solve sensitivity equation with respect to a large number of parameters, you can either solve the forward sensitivity equation for those parameters, and for each one of them you get this column. Obviously this is expensive to solve because you have to solve a PDE for each of these. So instead of solving this forward sensitivity equation, adjoint equation is preferred in a lot of these cases, because you only solve one. You solve the forward equation forward in time, and then you need to solve the adjoint equation backward in time to get all of these sensitivities. But basically you solve just one equation. But the challenge of adjoint is that you have to store the forward solution in time and then solve adjoint backward in time. So this forward backward flow is not desired, because you have to store and read the data from the disk, and for massive simulation that could be problematic. So we look at this problem as a matrix differential equation again, because all of these sensitivities are instantaneous. This you can form it as a matrix. And so if you look at that, so these are actual sensitivities of a reacting system, and you can see these sensitivities are highly correlated to each other. And just visually, you can look at this. So this is what we say, this matrix is instantaneously low rank. And so the idea is, how can we use a time-dependent basis to derive a low rank approximation for this? So the details of this approach, you can find it in this paper. But this is, so this method, if you see it in the slides, referred to as FOTD. OTD stands for optimally time-dependent decomposition, but these are all time-dependent bases. But time-dependent bases apply to linearized sensitivity equation. And so basically you have a set of orthonormal bases in the physical space. And now in this case, these Y coefficients are the sensitivity vectors. So this with respect to the number of parameters. So the size of each of these rows, D is the number of sensitivity parameters. And if R is much smaller than D, that's when we get a computational speed up. So the way to formulate this problem, and you see that throughout my slides, is that if you replace this low rank approximation into the full order model. So here the full order model is the sensitivity equations without doing any reduce or minus. So in this system, we get all the equations. This is the full model. If instead of V prime, we replace this with UY transpose, because UY transpose is a low rank approximation, so you see this is approximate, so this is not equal, there is an error. So that obviously this UY transpose is not going to satisfy, it's not going to be able to satisfy this equation exactly. As a result, there will be a residual that we are satisfying that equation. And then we form a variational principle by minimizing the residual. If you look at this term here, this is the residual term, where we have the left-hand side of the equation minus the right-hand side. And this is just simply this equation with V prime being replaced by UY transpose. So this is the residual. We minimize this residual by changing, by optimizing time derivative of Y. So basically, how should I update? Time derivative means updating these orthonormal vectors and their coefficients such that the amount that I'm violating the full order model is minimized. So that is the variational principle. And obviously, we have constraints here. The constraint here being that these modes, we want to keep them orthonormal instantaneously. And the orthonormality, that means the inner product of these modes. So that's what we mean by orthonormality. And if you solve this variational principle and minimize, and this is a convex loss function, you may call it. And if you take the derivative of this loss function with respect to this U dot and Y dot, then you get evolution equation for both of these two components. So this is an evolution equation for the special modes. This is an evolution equation for the coefficients. Obviously, the two are tightly coupled to each other. And even in this case, even though the system is linear, these equations are nonlinear, but they are coupled to each other. And basically what these two conditions mean, these two equations mean, is that if you solve these two equations, you're satisfying the optimality condition of this variational principle. So that means if we solve these two equations, we are minimizing this residual, which is an instantaneous residual, and we move forward. So that's what derives the evolution of the subspace. I'll get a little bit into more details of that even in the examples. And when you solve equations. And for this linear system, you can actually solve the equation that the computational cost of solving this equation is exactly equivalent to solving R of solving R forward sensitivity equations. That would be right, ideally, because we need to solve PDEs for the special modes and also ODEs, as you see here for this coefficient. But for linear system, you can exactly get the speed up. Well, I'll talk about when you get to a linear system, it's not like that, and you have to do something else. But for linear system, you can do that. So let me give you an example of that in the context of reacting flow. This biologically reacting flow is not turbine combustion, but it's just a demonstration. So this is, here we have 23 species, and then we consider perturbing each of these reaction parameters. So all the reaction parameters, and there are 34 reaction parameters here that are perturbed. So the goal is to solve this system. So if you look at the system, it's not really a matrix, is a tensor evolution equation, because if you look at each of the species, sensitivity of each of the species, this would be the column where each column, these are the rows of that column, or they correspond to the grid points, but then you have different parameters and different species. So in total, you have 20 species times 4, or we have 782 sensitivities that need to fall. And these different species parameters for modes are normal modes that correlate the structures and the corresponding coefficient. So if these are correlated, so remember the D here is 782, but let's see if we can approximate this with a smaller R value. And so these are the results. So you see, this is the relative error. So we solved the full 782 sensitivity fields so that we can actually look at the error and analyze that. And then when you see opt here, that once we did 782 of the matrix, that rank R equal to 2, and then compute the error. So this is the perfect error. So you won't be able to get below that error, because that's the optimal error. We also solve the sensitivity equation using this kind of reduced order modeling, which is shown by FOTD. So this is the relative error. So first of all, this is, you see that the FOTD and the optimal error. So FOTD closely follows the optimal error. So in that sense, this is great, because that's the best you can do. And the fact that you're close to the lower bound, it's a good sign. And moreover, you see that with increasing R, error decreases quickly. And that's because the system is instantaneously low dimensional, although if you look at this in a time averaging system, is very high dimensional. And also here, we are computing the instantaneous single value obtained by this low rank approximation, compared with this instantaneous optimal low rank approximation. And you see we have the singular values match really nicely, especially the very first singular values, and the last one usually do not match, because this FOTD, this is a reduced modeling. This is not going to exactly match instantaneous SVD. But in the FOTD formulation, we do not do any SVD. There is no data generation involved. It's just solving those two equations. Okay, so and so here we show actually 5 modes. You can see here with 5 modes, you can approximate the sensitivities with less than 1% error. So this nice here is that the first forward equation. So you compute these sensitivities with respect to forward. And these are the shape of the modes after normal modes. These modes advect with the flow as the flow goes from left to right, and they're orthonormal, and the higher modes capture smaller and smaller features as expected. And then you can reshape the Y vector here. Y vector is a vector of size number of species times number of parameters. You can reshape it back to a matrix, and you can see which species, what species is sensitive to which parameters, for example, immediately. And so this is also a time-dependent matrix. It's a vector that is matrixized. This is the first mode visualized. So this is quite interpretable. You can see a lot of species are not sensitive to certain parameters, but they are sensitive to some other parameters. This is the nominal speed up that the reduce or mine offers. And ideally, you want to be able to reduce the cost to just solving R modes equivalent to R vector of that matrix. And in the linear case, it's with some care in the way you write the program, you can achieve that nominal speed. All right, let me get to turbulent combustion. And turbulent combustion is also, you can formulate this as a matrix differential equation, where, as I said in the beginning of the talk, the matrix, the column of the matrix are the species mass fraction. And then you can, now here in this case, I'm considering a triple decomposition. Like I said, you shouldn't confused by whether I use the triple decomposition or like the previous sensitivity was using a decomposition. Both of these decompositions are exactly equivalent, and their differences are only in the numerics, but not analytically. So okay, so let's see and follow those steps that I showed for turbulent combustion. So the first step is just to write the equation as a matrix differential equation. So this phi is the entire the matrix of a species, is the whole thing, and then you can we name the right hand side as M, which is the entire right hand side, which has the advection, diffusion, and chemical source term. And then again, so if instead of this phi we replace this low rank approximation, which is basically instead of this phi replacing these triple matrices into the full or mole. Because there is error here, right? This is a low rank approximation. This is not going to be exactly equal to that. Because of this error, this approximation cannot satisfy the full or mole. As a result, there will be a residual. And so if, again, you minimize this residual with respect to the time variation of these three components, all three, and say, how can I update my bases in the physical space, as well as basis in the compositional space? And you can think of this as really the coefficients or amplitude, but this is essentially, if you diagonalize this matrix of singular values, how can I update all three components simultaneously such that this residual that I'm violating the full or mole is minimized? And again, you can actually follow the same procedure. And so there are two constraints here that I'm not showing all the details here. All of that details can be found in this paper. But you can, but there are two constraints here. Is that one is that these modes should be orthonormal, so that you can also incorporate this, and also these vectors in the composition should be orthonormal. And there are rules how you can set these constraints and to the composition. Once you enforce those constraints and you solve this optimization problem, you get this evolution equation. Again, this evolution equation, you don't need to solve any nonlinear optimization problem. Just the fact that you solve these evolution equations, that means you're minimizing these. So the optimality conditions are the evolution equations for these three components. And so you get a PDE, a set of PDEs for evolving the modes. You get two ODEs, one ODE for this matrix, another ODE for this matrix. So these are all of these three are also matrix differential equations. But you get these terms, which I will discuss a little bit in more detail in the next few slides. You get these kind of money, you get projections to the complement of the spaces spanned by U. So if this is a space spanned by U, this kind of operator projects this F, whatever vector you put in front of that basis, to the orthogonal complement spaces spanned by U. And that shows up in both of these basis evolution equation. And I will try to give an intuitive explanation why that is the case. Why do we get these orthogonal complement projections? But what is also so interesting is that you can actually use the very same principle I explained to derive even PCA transport equation and evolution equation. In fact, so we call this a unified variational principle. In fact, the same residual minimization principle is also applied in the PCA. So if you look at the PCA, which is a data-driven reduce or modeling, right? So PCA, we perform high of the flow, turbulent combustion, and we find this y, which is the composition vectors from data, right? So this y hat here is found from data, and instead of orthonormal, but this is obtained by an SVD, and then we, instead of phi, we replace this expansion, this low rank approximation. And you can, in fact, show very easily that the PC transport equation is a residual minimization, can be obtained from a residual minimization as well, where you minimize with respect to u dot. So y hat is out of the picture because we have already found what y hat is. And what you get out of this is just PC transport equation. Here, just to compare, and so you can also do this by decomposition for time-dependent basis here. And here, the difference is that this y is time-dependent, where y here is obtained from data, but here, this y tilde is not obtained from data, and it's orthonormal. And so now you can formulate variational principle, but basically the difference is that now the composition subspace is also included in the residual minimization. And in fact, this is like another degrees of freedom to minimize this residual in addition to u. And just by intuition and you can show it by rigorous analysis that adding this, we can achieve lower residual than just fixing this from data, because this now evolves. And so what you get out of this system, you get an evolution equation for the modes and an evolution equation for the subspace. And like I said, you get this term that I will get to and explain. And this is the formulation DBO, that the triple formulation that I explained. Like I said, these two formulations, the reason I am putting this formulation here, because it's really easy to draw analogy with this formulation and PCA formulation. It's not so straightforward how this is related to PCA, but we were trying to better understand and connect the difference between this kind of time-dependent basis versus a static data-driven subspaces. And I think this is really a really elegant way of understanding the difference between the two the workflows and the different types of reduced error modeling. But actually, they share a lot, in fact. And this can be thought as just updating subspace to minimize the residual, where here, basically, if you force y tilde to be 0, you recover PCA in this equation. This equation is exactly the same as that. And the nice thing is that you can show this equation are exactly equivalent to this decomposition. So whatever analysis we do here can be applied to the other decomposition. So, but like I said, this makes it easier to compare the two. So let me get a little bit into the weeds here. So whenever we do dimension reduction, like I said, there is always the residual. So if this is the right-hand side of the governing equation, at each instant of time, we can look at this vector as being somewhere out in the full order model. So here I'm visualizing the composition subspace. And in PCA, we have this YPCA, which is obtained from this subspace in the composition that is extracted from data. And you can write this M as a projection to this subspace and also a projection orthogonal to this subspace. This red part is the residual that is just neglected, right? So in any reduced order modeling, we will always have a residual. Whether we do time-dependent basis or static basis, there is always a residual, right? So this is the residual that gets neglected. If you look at the right-hand side of the PC transport equation, if you replace the PC transport into the full order model, then you can actually write it as you can decompose the right-hand side, just add and subtract this term and show this is the error. And when we project both sides to y, this gets basically, this vanishes and you recover the PC transport equation. But basically that's the residual. Whereas here in the time-dependent basis, if you look at this, again, you still have the same residual, but in a time dependent basis, if you apply time-dependent basis, these subspaces itself, the yellow plane, actually changes in time and varies in a way. And if you look at the evolution equation that is obtained, you see this term actually there, this I minus YY transpose. Basically, it tries to minimize this residual in a least square sense by optimally evolving this subspace. And so that's the important, because remember, we included this y dot in the minimization principle, in the variational principle. But you can see this evolution equation actually has, in a least square sense, tries to minimize this red part by optimally evolving the subspace. And you can even further show that the part that causes rotation in the y, if you have linear terms with and also equal diffusivity, constant diffusivity for all the species, the only term that causes this rotation, triggers this rotation, is the nonlinear term. In fact, the linear terms do not require any rotation. So if you have if m was just linear convective terms plus diffusive terms, where diffusive terms have constant diffusivity, then you will see actually this results in dy dt exactly equal to 0. But the term that triggers this is nonlinear term, and that's not surprising, because we know whenever we do reduced order modeling of nonlinear differential equation with the linear subspace, there is always this residual, and so but in this time dependent basis, this residual try to minimize that. So this is the application of this approach to which has 53 species and 325 reactions. So these are the DNS results. Here we show this low rank approximation with rank equal to 6. And so this is just to show the error analysis. We haven't done anything in terms of reducing the cost. I'll talk about the cost here. The cost of this becomes a lot more involved when you go to this kind of nonlinear equation. And this is the comparison of, so and the IPCA here is the instantaneous PCA, where which is the optimal, right? Remember, the instantaneous PCA is when we perform direct numerical simulation, we store the data, we do perform instantaneous SVD or instantaneous PCA, each snapshot. That would be more low rank subspace composition space. And TDB is this basically visualization of these vectors. So one of these vectors is this is the first vector, this is the second vector, and a third vector. Only thing we do, we rotate it so that these are energetically ranked. So this is a level of post-processing. You see PCA. PCA, the blue lines are the static, because they are as you can see, the TDB and IPCA follow each other very closely. Again, that's a good sign, because we are tracking the optimal subspace. Let me play that again. And you always see more variations in the higher mode. So you see this the composition space changes and adapts on the fly, and this is all based on that residual minimization. And so you can do further analysis, and this is what we always do. We look at the, like I say, instantaneous S singular value of the full order model, which are shown by the black line here, and that would be the reference. And we show that this kind of reduced order modeling, this is not, like I said, data-driven reduced order modeling. We just solve those equations, and that's it. There is no other way of enforcing that to be equal to the instantaneous PCA. But you see the leading singular values match very well, and you always see discrepancy between the lower singular values, because there is a memory reduced order modeling error involved in TDB, but that doesn't exist in IPCA, of course, because that just applies SVD on the full order model. And these are different metrics. So of course, this is the DNS, this is joint PDF, a mixture fraction with mixture fraction and OH. And so this is DNS, and you can obviously convert. So R equals 6, you see some discrepancy, but with R equal to 8. So you converge, actually. So in fact, if R is equal to full number of species, you recover the full order model, of course. And so this is the application of that. This is we just first column as the reference. This is mixture fraction DNS, but just showing the physical. I showed it in the previous slide. In the position is in the physical space. This is the U part. But U in this case will be 3D, and this is just showing that as this system evolves, the subspace also evolves with it. And it captures the structure here. So this is the reduced order modeling, this is the full order model. I don't know if I have time to cover another test case. I want to get to the cost part. Let me just skip this example in the interest of time. This is from Dr. Jackie Chen's group who have implemented this. This is very quickly, this is the 39 species end gas ignition to detonation. And what I want to show, let me just quickly show this result that this is, you will see at the end of this wave gets propagated from right to left, you see huge change when this gets close to the wall. And I'll show you the composition space. You see a significant change in the composition space as well corresponding to that. And these are the kind of problems that are really notoriously difficult to get with static subspaces. Let me show you the Y coefficient for this. Just pay attention at the end. These are the first mode and the second mode. And you will see towards the end, these are the major species. They will change significantly as this animation goes forward. Always the lower modes vary with time, but not the high modes all the time. But this, you can see actually at the end, right here, this is a huge rotation in the composition subspace. So that means if you wanted to approximate this with a fixed subspace, you have to consider both this regime and the previous regime, or you have to have a way to adapt this. Okay, so let me get to so I haven't talked about the cost, right? So, which is the part that we are working on, and it's really not easy to achieve the same saving in cost when we apply this to turbulent combustion. So let me get a little bit into the weeds and in terms of what is causing the cost issue, right? So I'll go back and I'll talk about this in the more generic context, and because it's just easier, and in the context of especially UQ, that we'll talk about another application, but also talk about the underlying issue in terms of cost. When you apply this kind of reduced order modeling to generic nonlinear PDEs, matrix differential equation, where combustion is being one of them, in fact, a tough one, you have all this issue. In fact, that's not the only issue. You have these 4 sets of issue. There is a sigma inverse in the right-hand side of this governing equation, which you don't get in like a PCA type dimension reduction, but here this term shows up here. That causes that, in fact, if this singular value is becoming small, this matrix of singular value can become singular. And we have recently addressed this issue, but I don't have time to cover all of that, but this is an issue. Probably the cost issue is that whenever you're solving this 3 evolution equation, this F here is the entire right-hand side of your matrix differential equation. You have to apply this F to this low rank matrix. So this F is the nonlinear map, right? In the combustion example, it involves the chemical source term, advection, and diffusive terms. You can handle advection diffusive terms very efficiently because those are linear terms and actually gain cost. At least advection terms, you can always do that, but diffusive terms, you still have to be careful, but not the chemical source term. The chemical source term, you basically have to compute the source term for all the full order model and then come back and project it to this, which is a challenge, right? So in fact, the very same challenge exists in PC transport equation, and that's been resolved usually by training a neural network model in the offline stage for the chemical source term. But the neural network is trained on the Y variable as input, and then I'll output the reaction rates. And so, but so that's obviously one way to adopt it here, except that here in this case we cannot train a neural network for a time-dependent Y, so that the input to the neural network has to be full order species. That's one way. We are trying to come up with other approaches such as hyperreduction to see how we can reduce this cost. We have been able to reduce this cost for generic nonlinear differential equation in the context of uncertainty quantification matrix differential equation, and also we have had some progress with respect to combustion, but I would say that's a still work in progress. So there are issues. This stability has been addressed also in this paper. The rank adaptivity has also been addressed by other authors as well in different applications. I want to talk about this paper that we issued, this very issue of cost, that this is actually quite costly to compute. And so how can you reduce that? And the fact that if you want to get efficiency with these models, you have to do an intrusive implementation. This approach here actually addresses both intrusiveness and cost. And so I want to talk about that. So more details about that, you can find it in this paper. This is applied to UQ, but it's the same principle that we are trying to apply to combustion as well. So let me motivate this by UQ. Like I said, UQ is also, you can write UQ as a matrix differential equation, right? Where this right-hand side of the governing equation, let's say you have a deterministic dynamical system, but you're perturbing the right-hand side with either initial condition or some random parameters. So then you will turn that into a matrix differential equation, but you have this f of v, which is, like I said, that is the source of cost, right? Just computing this. These other parts are not contributing to that cost, but it's just, this is the part that we need to resolve. How can we compute this f of v in a more efficient way? So really the objective of all of these kind of time-dependent low rank approximation is to be able to reduce the overall cost to just solving full or mono for R samples. That would be the ideal cost, right? Because we are sampling R columns, so we are solving PDEs. If we can reduce the cost of this to just solving R samples, then that's what we say we have achieved computational speed up. So in this case, in the context of combustion, it's roughly equivalent to saying reducing the cost of this to solving for R species. But I mean, depends what species they are, because if you pick different species, you get different costs. So it's really harder to make the same kind of exact precise statement in the context of combustion. But in the context of UQ, it's very easy to make that statement because each of the columns are completely independent from each other, because these are random samples of the dynamical system. So really the essence of this is based on hyperreduction, but we have developed this hyperreduction, on-the-fly hyperreduction basically for matrix differential equation, and that's based on this beautiful COR approximation. So COR approximation is a matrix low rank approximation where you only sample, if this matrix G, this is just the gist of it, if this matrix G is of rank R, you can approximate this by just sampling R columns and R rows of this matrix. And this matrix is exactly the columns of this matrix is the exact rows of that. And this is, and these kind of approximation differ on how you compute this middle matrix. We are using interpolatory COR. That means this matrix is exactly all these crosses that you see here inverted. So it's a very straightforward matrix. Although you shouldn't apply it in this form, you have to do the right numerics to get it working. But this is the essence of it. So what this tells you is that if this is, remember, the issue was computing that F, which is in the right-hand side. And that F is, you have to, the size of that F is the size of full or more. You want to avoid that. So the way we are avoiding that, we are only sampling that at these columns and rows. But the accuracy of this kind of low rank approximation to this matrix critically depends on what choice you make for the columns and rows. And we will use a direct empirical interpolation method to guide us where to sample this, and where actually these samples, all the columns and rows, so the way we sample them, they're time dependent, so they are not fixed. And we find them, we find which one of them to sample on the fly. So if you look at the entire matrix of the right-hand side, yeah, basically, we can combine those triple matrices in the previous slide as two matrices. One matrix that is orthonormal matrix of the column space of this matrix and the coefficient. If we can approximate this matrix with this multiplication of these two skinny matrices, we have accomplished a reduction in cost, because we haven't, any part you see in gray is not sampled. And the fact that we are not computing anything here, we can, instead of doing order of n times ns operations, you do order of n plus s. And that is the key. So as long as this is low rank and p is very small, then this can be very, and you can control the error of this approximation in a rigorous way. I don't have time to go over all of that. I'm not going to cover all of the details of this algorithm, but there is a really nice and simple algorithm to implement to know which columns and which rows to sample. in terms of sampling, I talked about the dime method. So, but once you do this, let me explain this. Once you, instead of F, if you can approximate that with UFZF transpose, you just replace that into your governing equation. And now each of these operations are small operations. And so once basically the entire cost is just sampling that equation and computing this UF and ZF. Once you have that, then you can decompose that and bring UF to the U inner product parts and ZF to the Y inner product parts. And then these operations can be done extremely quickly. And moreover, you never form that full matrix, so you save also on memory. And that's also, it's not just the CPU, it's also memory. And also, you don't need to do a term-by-term derivation of these equations like an intrusive way. You basically sample the right-hand side of your full normal at the selected columns and rows. And there are other approaches for finding out where to sample. This is based on beautiful work based on leverage score, but you definitely get much better. This is a statistical approach to sample columns and rows, but you get better accuracy with deterministic approaches. Also, you can apply this to this is separate than the sparse sampling. You can make this methodology rank adaptive by looking at the residual of that you get at the right-hand side of every time instant, and look at the norm of that residual relative to the norm of the right-hand side. And if that is larger than some value, actually can add modes or remove modes. So R, you will see in the results that I will show, R in fact is also time dependent. So the rank of the system doesn't have to be fixed. It varies according to the dimensionality of the full normal. All right, let me show you some example here. This is application of this to advection diffusion reaction equation where this diffusion coefficient is random. And you see these sample points. This is just one of the samples, but you see these dime points and these are leverage score points. They're strategically located. So this is like sweeping the rows of the matrix. So you sweep these rows at these blue dots, and you see they actually advect with the flow, and they strategically sample the part of the flow that matters. And so that's the key. Remember, in the other, if you don't do this, basically you're evaluating the rows of this matrix for all the points, but you'll only do that for a fraction of number of points. So that's how you can get computational speed up. So this is with 50 samples. I'll show you an example. We did it with 100,000 samples. So this is with 50 samples, and this is now rank adaptive. So here the column of the matrix are the random sample of that Monte Carlo random sample of that PDE. And so you see now the rank is adaptive, so we add modes, and so the modes keep added, so the rank actually starts out small and then keeps growing. And this is the overall error. So here, we did a 50 sample because we wanted to compare that against the full normal, because we also solved the full normal for the 50 samples. We computed the SVD of that to compare. We also did a case for 100,000 samples. In this case, we couldn't actually solve the full normal because solving the full normal would be equivalent of solving 100,000 PDEs. So, but we use this algorithm that I just presented. We solved that on a laptop. And in fact, the laptop doesn't have memory to store that full matrix. So this is just evidence of like the fact that we never formed this full matrix during the computational workflow, and we always worked with these low rank skinny matrices. And so that way, as long as you store this in this form, you're actually saving on memory because you're storing R field, and these two are not that expensive to store. In the case of UQ, this could be each row here has 100,000 samples, but you only store R of these. So R of these rather than the multiplication of these. So instead of N times NS, we store N plus NS. And that's how, if both N and NS are large, that's how you get an order of reduction. And for the mode adaptivity, you can put different threshold and see what you get. So how much you want to add modes depends what fidelity you want to have in the residual. This is the threshold we put on the residual in the right-hand side of governing equation. So this will enforce that the residual doesn't get below, it doesn't get above 10 to the minus 4. And you get this rank that is equal to 2 initially, then goes to 3, and then 4, and stays at 4. If you crank this up, you make this lower, you make this more higher rank, and you see the rank actually increases more rapidly. And if you do 10 to the minus 10, the rank increases also. So this equation is a generic nonlinear equation, right? So and so now we are actually applying this to, okay, so this to turbulent combustion. This is we've made some progress here. In turbulent combustion is more difficult to get the same efficiency we get from the UQ example. So like I said, this is work in progress, but just show that the fact that in terms of error, that because this adds another level of error to our approximation, because we also are approximating right-hand side as also a low rank approximation itself. So this will introduce an error just to test that whether that error will destroy anything in terms of combustion. Here, this is the full or null, which is DNS. This is the one without doing any of this. This is for GRI mechanism. These are temperature contours. Let me just pause this. And this is without doing any sparse sampling. This is instantaneous temperature contours, and this is with doing a sparse sample. And this actually shows you where the sparse sampling points are happening. So these are also, so these are points. So when you apply this to combustion, the rows are still physical points. When you sweep the rows of that matrix, sweeping the columns is the difficult part, because in combustion, the columns are mass fraction of these different species, and they're non-linearly connected to each other. And that's the part that we haven't been able to achieve that much, the kind of efficiency gain we get from applying this to UQ problem. But here in the CPU implementation of this, we were able to speed up the computation by a factor of 2. But it's still not impressive. So that's why I think this is a work in progress, and we are working on addressing the cost issue here. But in the context of combustion, most of our work has focused on just establishing that this kind of low rank structures exist in the combustion problem, which is not a surprise. People who have been doing excellent work in PCA, that has been known, but a lot of machinery have been developed for PCA, and we are trying to learn from that as well. But this is again the comparison of doing SDBO is a sparse DBO, and DBO is like not doing anything. So we just show the error. We compare the error with the end. So you see the order of error doesn't change, but doing this is sparse sampling. But obviously we add some more error because we are doing that, right? So, but here doing that, so this is the number of columns we sample in the right-hand side. So the number of columns is also adaptive. So this is GRI mechanism, which has 53 species. So there are 53 columns in the right-hand side. So this is how many columns we sample over time. So 10, and then that changes according to the accuracy, and using those error criteria that we have, we find this adaptively. All right, with that, let me conclude. I think I'm a little bit over time, but I haven't crossed the 10-15 upper bound. So I'll just leave this to stay here. I think I already summarized this, and I just want to get to the questions. But I think in terms of UQ, we have made a lot of progress to actually apply this kind of methodology to any nonlinear dynamical system, as long as the rank is low, right? So see, that's a huge if. So if the rank is low, we can do this. If the rank is not low, we have to do other things. But in combustion, that's still work in progress. These are postdocs, former postdocs, or PhD students who contributed to this talk. And with that, I will take any questions you may have.
Thank you very much for this very nice presentation. Thank you. I think there is we have time for questions, so I would actually ask the people in the meeting to raise their hand and ask questions. Who is the first one who dares? I will maybe start. I think it's very interesting. One question I have, I was wondering about Hessam, is how do you, I mean, is there a way you can actually modify the dimensionality during the simulation?
Yep, that's correct. How do I do that? So is that the question?
Yes, I was wondering because it might happen that the run or the dimensionality of the problem should change, or I don't know.
Exactly.
And yes, okay.
Yeah, so it's the residual of solving this matrix differential equation with this low rank approximation. You will have a residual at each time instant, right? So at each time instant, because like I said, this is a residual minimization. And you can compute that residual, actually. You can compute that using this sparse sampling. This F orthogonal is the part that you cannot approximate at that time instant with this low rank approximation. So this is, with this sparse sampling, this is cheaply computable. So once you compute that, you can see, okay, this is how much I'm missing out at that time instant. And you have to use a relative criteria. So that's why we normalize it with the Frobenius norm, however we approximated that F. So this is also cheaply available. So we compute the ratio of these two Frobenius norms and say, okay, if this relative residual exceeded this number, which is we denote here with epsilon u, then add a new mode. But the adding, so that just says what mode to add. But we actually have shown that it's important to know what is the direction of the newly added mode in the U space, in the Y space, what singular value it should have. And those are, you can show that those are exactly the SVD of this part of the matrix. So if you decompose your matrix to the part that is already covered with your low rank approximation, that is, and the part that you didn't cover, the SVD of the part that you didn't cover, the first mode of that gives you the initial condition of the new mode that you need to add.
Okay, it's very clear. Thank you.
Of course.
So I have a follow-up question.
Thank you, Camila. Yeah, please.
So I wonder if you've noticed any kind of physical intuition behind where the dimensionality has to increase. Like, have you noticed that it has to increase, for example, in regions where there's a lot of chemistry happening?
Yeah. In fact, maybe not physical, but I'll give you a mathematical explanation because I think that's probably, that's the way to get to the physics. Like I said, the reason the residual is actually because of the nonlinear chemical source term in the right-hand side. And so that observation is critical. And if this chemical source in the right-hand side, that is the part that is creating the residual. And with time-dependent basis, you can reduce that, but you cannot completely eliminate that, of course. So when this S has a huge part orthogonal to this subspace, that's where you have a lot of error, and that's where you have to crank up the rank. So it's definitely coming from the chemistry. But I think one could probably start analyzing this, and we haven't done that. But I think that's an excellent question to see what part of the chemistry we were missing. Because with these projections, you can see, okay, this part we captured, but this part was way outside this subspace, and you need to enrich the subspace by adding more. So we haven't done that, but I think the key to get to that is through this equation.
Right. Thank you.
Thank you. Any other question? I know that Salvatore, you have a question?
Yeah. I would like to ask a question.
Sure.
It might be a bit of repetition because the connection was a bit spotty, but you mentioned neural network at some point. I guess to introduce some kind of nonlinearity into this approach, which is a linear approach. So we want to compensate for the fact that source terms are non-linear. So I wanted to ask if you could repeat where a neural network or any kind of regression model, a GPR or whatever, can be integrated in this approach to ameliorate the representation, the low rank representation.
I have to say it's more difficult to apply those kind of things to this time-dependent basis that we usually do for PCA, because in PCA that Y is static, and so you can actually do that kind of neural network training in the offline stage. Whereas here the Y actually swims in the entire space. So I think if there is any sort of neural network representation, and I don't know actually how that can be done. So I don't know the answer to your question. But when I talked about neural network, it wasn't in that context. It was, I know, so there are neural networks are used in two ways in PC, I'm sure you know, but let me just, the context I was talking about is just to approximating the chemical source them in the right-hand side so that you speed up the PC transport evolution equation, not the fact that we use GR or neural network is used to reconstruct linearly back to the full order model. So that part, I still do not know how we can do that. Probably you can train a neural network with the full order species because this will reconstruct the full order species, and that way maybe. But I don't know of any really rigorous way of doing that. So that's why that part we haven't done that nonlinear reconstruction. Basically, the decoder, a nonlinear decoder. But that's interesting to see. I would, yeah. So, yeah. Short answer: I don't know how to do that. But when I was referring to neural network, it was just in the context of learning the chemical source.
Okay. Yeah. Thank you.
Of course.
And I guess if I may ask another question.
Sure.
I mean, these approaches, you know, very high potential, very great potential, and let's say we are able to solve all the problems that we have, like kind of sorry, one moment, I've interrupted. Okay, let's say that you know, we are able to, this works perfectly and we get a reconstruction error that is very, very low. Then, well, what will happen to CFD? It's it's gonna be you know, will it be used in like in 20-30 years if we have you know, a complete you know, low-rank approximation? Then you know, what will happen to CFD? Will this kill CFD or?
Oh no, I think this is, to me, the way I see. No, not at all. I think this is, in fact, what I think is interesting about this kind of reducer modeling is, in fact, it's very much connected CFD or broader computational science, right? So basically, you have to solve. If you see behind this, we are utilizing a lot of fantastic developments in CFD. It's just the way I see the potential of this is that the way we do CFD, we always choose a basis, right? So that, I mean, that's the whole for any reducer modeling. That when we do CFD, choose a basis, and based on that, we go and do computation. But I think there are better ways to not choose the basis and let the governing equation tell you what to do. So basically, adding that adaptivity, I think that is the part that I see the potential of this. So even, in fact, we are trying to solve even the Navier-Stokes equation for these BT spaces, and we are making some progress just doing Navier-Stokes equation, not a reacting flow. And I think there is potential, but the way I see this is not replacing CFD, it's augmenting CFD. Yeah, I see a deep connection, in fact.
Okay, thank you.
I have a question, some curiosity. So I like very much of this approach that is not data-driven, right? So you don't need data. And this is, I think, a very big strength. On the other end, the PCA-based approach can profit of the availability of data to work a little bit on the source term and get the reduction. And so this is actually a very genuine question that I ask myself. Is there a middle ground where we can actually think of a kind of a hybrid approach that can take the best of the two?
Absolutely. That's an excellent question. I love that. And in fact, we have already worked on that. So you can augment these bases with the data-driven basis. And that way you will do a lot less computation for PCA. Yes. So there are, I see a lot of in the middle ground, probably that's where the sweet spot is. That, let's say you ran some chip simulation, you generated from 1D case, you generated Y from PCA. It's not that difficult to incorporate that into this Y. And then that way you will only advance for only a smaller number of modes that is orthogonal to that subspace. That way you have all the machinery of PCA, but this way, you also evolve this subspace to make sure that whenever that PCA subspace was not appropriate, you are actually, at least you have a way of adapting to that condition, right? So that's why this equation is very interesting in my opinion, because this is exactly PCA. So you can put PCA, Y of PCA here and see how much that's being violated. And you can turn it on. So I see a lot of scenarios that can be used, but one basis augmentation, one way is to adapting the PCA basis only for a few time steps or whenever things are going wrong. So that way you have some guarantees, right? So there are a number of interesting scenarios that this kind of formulation give you flexibility with respect to PCA. And so maybe you're happy with PCA for 90% of the simulation time, but there's only 10% where things go wrong because of this residual. That way you can actually use this kind of methodology to adapt that. That's one way. And then, like I said, there is another way to augment the Y of PCA with only a few modes, because you already cover our very good modes with PCA. So just augment that with maybe 2 modes that is orthogonal to that, but let them to be time dependent. Then you have to derive new governing equation for the time dependent basis here, because you have to make sure the governing equation is in the complement of the PCA, but that way you will do a lot less computation. Both of these sound very interesting to me.
Okay, very, very nice. I mean, I I also think a lot about this these hybrid methods. I don't know if there are other questions. I think not. So I will. I think we can close this first lecture here. I take the occasion to thank you again very much, Hessam. Thank you very much for attending.
Thank you.
Bye bye.
Bye bye.